Okay, it's kind of a strange looking integral we have here today. At first, it looked kind of tedious and I really wasn't sure what's going on with the square root of 3. Actually, I still don't know why that's really there. But anyway, the first thing I want to notice about this is it actually is an even function. Our definition for an even function is just that if we have f of minus x, this is going to be the same thing of f of x. And for this, we'll just group it all together. This will be our f of x. And if you just take minus x and you plug it in, here the minus goes away because it's squared, and here the minus goes away because it's absolute value. And so this check is going to work. And then using this, we've got this principle of even functions. When our bounds are symmetric around 0, the way they are in our problem, and we have an even function, we can just switch the lower bound to 0 and bring a 2 out front. So we'll make this change this to a 0 here, bring the 2 out. And what that's going to allow me to do is then we can drop the absolute value here because x is always going to be positive with these bounds. One other minor thing, let's just distribute this minus sign in. So if I distribute it in here, this becomes a plus. And then we'll just have a minus in front of the square root of 3 right here. So like I said, I don't know what the square root of 3 is doing there, so I'm just going to kind of ignore it. At the end, we'll integrate it, and it's just going to be a constant value. As far as I can see, I think the only reason they put that there was just to kind of confuse us. I don't think it has a purpose. If you found some purpose for that square root of 3, let me know in the comments. I'd be curious if there's another way. And then with it cleaned up like this, I just want to notice the similarity. If we think about this as we could split it into 3 integrals, and maybe let's focus on this. This is really similar to a problem I've done quite a few times in the past when we have this integral from 0 to 1. Again, it's a 1 here instead of a 4. This thing is just the unit circle. And you can see it's not really a perfect circle, but pretty close. But for this, the integral just represents the first quadrant. The reason is because, let's say this point here is 1. Our bounds go from 0 to 1. So we don't want the second quadrant or the third quadrant. And the reason we don't want the fourth quadrant is because the square root's always positive. So this region right here would just be pi over 4 because of the area of the whole circle would be pi r squared when the radius is 1. Pi times 1 squared is just pi, and we're just taking 1/4 of it. The reason this thing's a circle, and you might not recognize it, if you just set this equal to y, and you square both sides, not worrying about absolute value or any of that stuff right now, and then we bring the x squared on this side of the equation, you get y squared plus x squared equals 1. I should probably write it the other way. X squared plus y squared equals 1. This is just the equation of a circle with radius 1. So for this thing over here, square root 4 minus x squared, if you do this same kind of thing, you get x squared plus y squared equals 4. I can write this as 2 squared because this value is the radius of the circle. So now here with my second attempt on a circle, now this point here is 2, is our radius on this circle is going to be 2. We're still going to be interested in just the first quadrant. Again, square root's positive, all that. Now one catch on it though, if we look at our bounds on the integral, they're going from 0 to 1. So we're not looking for the whole first quadrant. I should get rid of this. If this point right here is 1, and we want the area from 0 to 1, then on just this integral here, we're looking for this region right here. So when I first did this, I'm like, how am I going to calculate just this area? I think there is a way to do it. There's some geometry you could do, but I don't think we need to deal with it because we also have this other integral or this other piece that's really similar, and we can look at dealing with this one. Now for this piece, let's square both sides, do the same kind of thing, get it in the form of the equation for this circle. Let's bring this piece first. Let me just instead of writing it as 1 plus x, let's write it as x plus 1 squared plus y squared equals 4, just rearranging this. But now for our equation for a circle that's not centered at 0, we've got a formula x minus a squared plus y minus b squared equals r squared. So the radius here is still going to be 2, of course. The b value here, that's just going to be 0. So our center, the y value for the center is going to be 0. But over here, the value that's going to work for a is going to be minus 1. You plug a minus 1 there, you get a plus 1. So now for the graph of this thing, we're going to have the exact same circle, same area, same everything, but it's going to just be shifted to the left by 1. And now looking at this graph, I'm kind of wishing I did this on a computer or something because it's going to look pretty skewed. But anyway, we're supposed to have over here the same circle, center here, the center of the circle is at minus 1, but here's 0 on our xy axis. Now by shifting it, the area we want is actually different. Again, our bounds are from 0 to 1. So what we want is the positive area. Square root's positive. So we want this area from 0 to 1, which is just going to be this part of the first quadrant. But now going back to our original problem, notice we're just adding this one and this one. Let's move the square root of 3 out of the way because it's just kind of confusing things. So now at this first integral here, when we add these two together, we're adding these two areas together. But putting these together, what we end up with is just the whole first quadrant, because we have this piece here, and then we're adding in the other chunk from our shifted piece. So if we put the whole area just on this one graph, we're adding back in this area right here. And what we end up with here is the whole first quadrant. So all we need to do for this integral is just calculate this area really quick, and it's going to be pi r squared over 4, because we just want a fourth of it. And so in our case, the radius is going to be 2, so it's going to be pi 2 squared over 4. This cancels, and this area right here is just pi. So really for this problem, it's just by visualizing the graph, it becomes a really fast problem, because this whole piece right here is just going to be pi. So what we get is 2 pi plus 2 square root of 3, integrate a constant, and we get an x from 0 to 1. And I made a mistake because this should be a minus sign. And so the 0 is nothing. And so plugging in 1, we get 2 pi minus 2 square root of 3. And I think I'll factor out 2. So for my final solution, we just get 2 pi minus square root of 3. And that's it. There you go. That's it for today. Thanks everyone for watching. Have a good day.